In this video, we discuss about the analogy of translation and rotational dynamics, rotational motion. For linear displacement, here we call the linear displacement. For displacement of translation motion, we call here the linear displacement. Linear displacement is represented by the s, and here is angular displacement, which is called theta. The relation between angular displacement and linear displacement s is equals to r theta, and velocity v for translation motion, which is a rate of change of displacement ds upon dt, and for angular velocity is omega, rate of change of angular displacement upon time taken, and relation is p is equals to r omega. And for acceleration, linear acceleration, rate of change of velocity upon time taken. Here for the angular velocity, angular velocity is alpha dw upon t, rate of change of angular velocity upon rate and time taken is angular acceleration. And for the mass, in the mass for linear velocity, the mass m is the analogy of mass in translation motion is here is moment of inertia. Relation I is equals to summation m r square. Linear momentum, linear momentum is equals to, the linear momentum is represented by the p is equals to mv, mass into velocity, and here I is the replaced by the mass and omega is the velocity. The angular momentum l is equals to I omega. And the force is rate of change of linear momentum, linear momentum dp upon dt. Here rate of change of angular momentum is torque, dt upon dl upon dt, and torque is given by the I here. This is known as dl upon dt, I omega, I, and here is alpha. And Octon for the Octon for the translation motion. Octon is force into displacement here. Here torque into dq is the angular displacement, and power for F into V, force into velocity, power, and here torque into omega, which is the velocity in the angular displacement. And kinetic energy is 1 by 2 mv square, and here kinetic energy is 1 by 2 I omega square. P is equals to U plus AT. It is from the kinematics, and this is the final velocity. This is initial velocity plus A, alpha refers to acceleration. W is equals to W. Omega is equals to omega naught plus omega final is equals to omega initial plus acceleration into time taken. B square is equals to U square plus 2as final omega square minus, and here is initial omega square, and 2 into here alpha into theta. Theta represent angular displacement and A represent angular acceleration. Here s is equals to ut plus 1 by 2 half at square. Here all the replace, theta is s is replaced by the theta, and w, this is the initial velocity, it is final velocity, it is angular acceleration, and st is equals to ut plus a by 2 2t minus 1. Here angular velocity is the relation the omega is equals to that we already discussed in the previous video, so I want to skip it here. First of all, we discuss here is moment of inertia. Moment of inertia is represented by the I is equals to mr square. It is the analogy of the mass. It is tensor quantity, its direction is different, and its SI unit is kg into meter square. It depends upon the size, mass, axis of rotation, distribution of mass about the axis, but it is independent in the angular velocity, torque, angular acceleration. Here For the discrete mass, I is equals to m1 r square plus m2 r square. It can be added as a scalar quantity because it is tensor quantity, and it can be added or subtracted like the scalar quantity. Here, force is equals to m into a. Here, torque is equals to m r square. Here, the m r square represent the I. I is the analogy of the mass, and if alpha for acceleration, therefore the torque is equals to I into alpha comes from here. And next one we want to learn is perpendicular axis theorem, which is very important. It is only valid in the two dimensional body or laminal plate. Iz is equals to Ix plus Iz. The condition required for to have the perpendicular axis is that the XYZ should be mutually perpendicular. They should be mutually perpendicular to each other, and XY should be in the plane of the body. XY must should be in the plane of the body, and Z should be perpendicular to the plane of the body. Z should be perpendicular to the plane of the body, and here Iz is equals to is the sum of I moment of inertia of y plus moment of inertia of x. The sum of moment of inertia of y coordinate and x coordinate is equal to the moment of inertia of Iz. And parallel axis theorem. Parallel axis theorem, I is equals to ICOM. COM is refers to the center of mass. We already describe or learn about the center of mass in the part 1 video of rotational dynamics. It is the center where the all mass is assumed to be concentrated, and D is the distance between two parallel points. Here in the parallel points, the new if there is given the ICOM inertia moment of inertia at the center of mass, and we can find out the this I from I for the sum of center of mass moment of inertia of center of mass plus md square. The condition required for the parallel axis theorem is two axes must parallel. One axis will pass through the COM, and perpendicular distance between the distance is perpendicularly, and distance may not be this like distance must be perpendicular. Here moment of inertia of uniform rod. we we learned in the formula tips, but how to make it easy to remember, and about the center of mass, we must have to remember it m square by 2 bell for the uniform rod. But for the ends, we use the parallel axis theorem. If there is two line are parallel, here two line are parallel if, and m l square plus we use the parallel axis theorem. The distance is l by 2 here. M l square, here is the this is the moment of inertia of center of mass, and plus and m d square. Here d square is l by 2. L by 2 is square, and we find the about the ends m l square by 3. And for the rectangular lamella, we must remind yam I is equals to yam l square plus b square. But if there is the axis parallel to, there is no movement of inertia. Here about the axis, this A is parallel, and here is no movement of inertia. I is equals to, we only calculate the where is perpendicular change. Here is perpendicular change because moment of inertia is the perpendicular change into mass, and here is no perpendicular change, they are parallel, so we cannot consider A is to get the moment of inertia for this. So for this, if A is parallel to the parallel, here I is equals to m b square by 2 bell. And for the For the if B is parallel to the B, your axis is parallel to the B, and then we skip the B, and m is squared by 2. This is moment of inertia for this, and this mb squared by 2 will is the moment of inertia when the axis is parallel to the A. And circular loop. For the circular loop through the center and perpendicular to the plane, I is equals to mr square. We must remember it. If the center of through the center and to the plane, for the circular loop, I is equals to mr square. This one we must remember. But from above through its in, we apply the parallel axis theorem. Here, the distance is r is square, and moment of inertia we already know about the center of mass I is equals to mr square. About center of gravity, I is equals to mr square. So we use the parallel axis theorem. Here we use the moment of inertia for these scenes are I is equals to ICOM, inertia about center of mass, plus ID square, mr square plus mr square. mr square here and mr square here is equals to 2 mr square. And about its diameter, for the about its diameter we apply the perpendicular axis theorem. About its diameter we apply the perpendicular axis theorem. Here, but for the easiness, about the diameter, each and every diameter, about the diameter there is the half about the center of gravity. If moment of inertia is mr square, mr square, and about the diameter it is half of the center of gravity, mr square by 2. But also we can use here perpendicular axis theorem to find out it. And about the tangent is parallel to the parallel to this axis. Tangent is parallel to its diameter. We know that diameter is mr square by 2, here mr square by 2. Then for this is parallel, so here is also radius r. Radius is r. Then we use the parallel axis theorem about the parallel axis for the mr square plus 2 plus mr square is equals to 3 by 2 mr square. And for the circular disc, we remember for the diameter there in this above mr square by 2, which is their diameter for the circular ring or circular loop. And for this we apply the parallel axis theorem here. mr square by 2 plus mr square is equals to 3 by 2 mr square. mr square for the center and mr square for this distance, and we find 3 by 2 mr square for the circular disc through its diameter. Through its diameter we already know that for the diameter the half of the center of gravity. If there is mr square by 2 in for the center, and here mr square by 4 which is half of the center. And for the tangent, it is parallel to the diameter, and we apply here is parallel axis theorem. We apply here parallel axis theorem. Here for the diameter mr square plus mr square by 4 plus mr square, here we get 5 by 4 mr square for the tangent of circular disc. For the hollow disc, through its center, m by 2 r square plus r square, and m by 4 r square plus r square. We must remember it here. For the diameter, here is a half. And for solid sphere, about its diameter, about its axis is about its diameter. We must remember is 2 by 5 mr square. About its axis is equals to about its diameter. And for about its tangent, about this tangent, we remember we apply the parallel axis theorem. 2 by 5 mr square plus mr square is equals to 7 by 5 mr square. About the tangent, tangent is parallel to its diameter. And for the hollow sphere, we must remember I is equals to 2 by 3 mr square. For hollow hemisphere, it is also called thin spherical shell. I is equals to 2 by 3 mr square. Here for the tangent, I is equals to 2 by 3 plus mr square. We applied here also the parallel axis theorem and we get 5 by 3 mr square. And for hollow cylinder, about its geometric axis, for hollow cylinder, I is equals to mr square. And for solid cylinder, I is equals to mr square by 2. And about its center and parallel to the geometric axis, L square upon 12 plus r square by 2, L square by 12 plus r square by 4. And here is some more additional information about the moment of inertia. If the temperature increase, moment of inertia is also increase. Moment of inertia doesn't depend upon the angular velocity, angular momentum, angular acceleration, torque. Raw egg is hollow, half-boiled egg, and earth is solid sphere. And some more information about the moment of inertia. Tensor refers to the mode direction. It can be added or subtracted like scalar. Moment mass into perpendicular distance. Moment of inertia is equals to mass into perpendicular distance. Here, when a particle lie on the axis of rotation, then the perpendicular distance a particle from the axis of rotation. When the particle lie on the axis of rotation, then the perpendicular distance of particle from the rotational is 0. So moment of inertia is 0. For discrete, I is equals to mr square. For the continuous, di is equals to dm ax square for continuous distribution.